There was a time when powerful oceans spread across large parts of the continents, when the skies were filled with insects much bigger than the ones we see today, and when massive volcanic eruptions quickly changed the shape of the land. This was the world of prehistoric Earth. From about 566 million years ago and onward, the planet was always changing. Huge sea creatures called trilobites crawled along the ocean floor long before the first dinosaurs ever walked on land. Over millions of years, enormous landmasses like Gondwana and Pangaea slowly came together, and later broke apart as continents crashed into each other. Thick forests made up of giant ferns grew even in areas near the poles, while dry deserts appeared in places that were once covered by oceans. Each period of Earth's history brought new kinds of life, and many of them eventually disappeared forever. The Cambrian period was the very first chapter of the Paleozoic era, and a major part of the Phanerozoic eon, the time in Earth's history when life truly began to grow and spread in visible and complex ways. This period lasted for about 51.95 million years, starting around 538.8 million years ago and ending around 486.85 million years ago, when the Ordovician period began. Back then, Earth looked very different. Most of the land was gathered in the southern half of the planet and surrounded by a vast ocean called Panthalassa. Meanwhile, a huge supercontinent called Gondwana was slowly forming. As its parts crashed together and joined during the Ediacaran and early Cambrian times, the movement of Earth's plates created new mountain ranges and volcanic activity along the edges. These changes helped increase global temperatures. At the same time, another landmass named Laurentia lay along the equator, separated from Gondwana by the widening Iapetus Ocean. But the most amazing thing about the Cambrian was what happened to life itself. Before this period, most living things were tiny, single-celled organisms, and their fossils are very rare. Some more complex many-celled organisms had started to appear toward the end of the Ediacaran. But during the Cambrian, something remarkable occurred: the Cambrian explosion. This was a sudden rise in the variety and complexity of life, leading to the first members of nearly all major animal groups we know today. What also makes the Cambrian special is its many Lagerstätten, rare fossil sites where not just hard shells, but even the soft parts of organisms were preserved. These layers give us rare and valuable snapshots of early life in incredible detail. The word Cambrian comes from the Latin form of the Welsh name for Wales, Cymru. It was in Wales that rocks from this time period were first carefully studied. In the year 1835, geologist Adam Sedgwick gave the Cambrian its name and divided it into three parts: lower, middle, and upper. He worked with fellow geologist Roderick Murchison to draw the boundary between the Cambrian and the layers above it, called the Silurian. At first they agreed, but this agreement did not last. Because early Cambrian rocks did not contain many fossils, Sedgwick used the types of rock to define his Cambrian layers. Meanwhile, Murchison found more fossils in Silurian rocks and used them to make connections across Europe and Russia. As scientists began to find fossils in older rocks, Murchison moved the Silurian boundary downward into land Sedgwick believed belonged to the Cambrian. This led to a scientific dispute between their supporters. Things became more confusing in the year 1852 when new field studies showed a clear break, called an unconformity, within the Silurian rocks. This change in fossil types allowed Sedgwick to claim back some of that land for the Cambrian. Still, the disagreement continued long after both men had passed away. Finally, in the year 1879, geologist Charles Lapworth stepped in. He suggested that the disputed layers belonged to a completely new period, which he named the Ordovician. The term Cambrian was officially accepted in 1960 at the 21st International Geological Congress. It now includes only what Sedgwick first called the Lower Cambrian, though it now also reaches into even older rocks. To compare rocks around the world, geologists use a system called Global Boundary Stratotype Section and Point, shortened to GSSP. These are exact places around the world where the start of a geological time unit is clearly shown in rock layers. The Cambrian period is now divided into 4 main parts, called series, and 10 smaller sections, called stages. At first, scientists believed the Cambrian began when trilobites, the ancient armored relatives of modern arthropods, first appeared. Later they discovered small shelly fossils and Ediacaran organisms that came even earlier. This created the need for a more exact starting point for the Cambrian. It was not until 1994 that the Cambrian period was officially defined. Scientists chose a place called Fortune Head in Newfoundland, Canada. The base of the Cambrian there is marked by the first appearance of a fossil named Treptichnus pedum, a type of burrow that shows more advanced animal behavior. Early estimates placed the start of the Cambrian at about 570 million years ago, but newer and more accurate dating methods now place it at 538.8 million years ago, with a small margin of error of about plus or minus 0.6 million years. This date comes from ash layers in Oman, which also show a drop in carbon-13 levels and the disappearance of well-known Ediacaran fossils like Claudina and Namacalathus. However, some researchers believe this site may not show the true boundary and prefer slightly older estimates of 544 to 542 million years ago. In Russia, many fossil experts prefer to set the start of the Cambrian at the beginning of the Tomotian stage, marked by the rise of hard mineral skeletons and the first Archaeoscython reefs. There were 4 parts of the Cambrian period, Terranuvian series, from 538.8 to about 521 million years ago. This is the earliest chapter of the Cambrian. It contains no trilobite fossils. It includes the Fortunian stage and an unnamed stage 2 marked by trace fossils and small shelly fossils. The name Terranuvian was made official in the year 2007. Cambrian Series 2 from about 521 to 506.5 million years ago. This part does not yet have an official name. It includes Cambrian Stage 3 and Stage 4. During this time, animal diversity increased greatly, especially among trilobites and archaeocyaths. Making worldwide comparisons is difficult because fossils differ from region to region. Meolingian series from about 506.5 to 497 million years ago, formerly called Cambrian Series 3. It includes the Wuluan, Drumian and Gujangian stages. It was approved in 2018 and is named after the Miaoling Mountains in China. This period begins with the first appearance of the trilobite Oryctocephalus indicus. At the boundary between Series 2 and the Meolingian, many trilobite groups such as Olenellids, Eodicids and Rhydlachides died out. This is seen as the first known large-scale extinction of trilobites. Furongian series from about 497 to 486.85 million years ago. This is the final part of the Cambrian. The name was approved in 2003 and replaced the older term Upper Cambrian. It begins with the appearance of the trilobite Glyptagnostus reticulatus. It includes the Pybian stage, the Jiangshanian stage, and an unnamed stage 10. The Cambrian Ordovician boundary is officially marked at Green Point in western Newfoundland, Canada. and dated to 486.85 million years ago. This point is defined by the first appearance of a tiny tooth-shaped fossil called Iapetognathus fluctivagus. In places where this fossil is not found, scientists use other markers, such as floating graptolites or the trilobite Jujujaspis borealis. Several large meteorites struck Earth during the Cambrian. Around 535 million years ago, a major impact formed the Neugrund crater in Estonia, about 20 kilometers wide. The Gardnos crater in Norway, about 5 kilometers wide, formed around 500 million years ago in a shallow sea. During the Cambrian period, Earth's climate was mostly warm and wet. Scientists know this from the types of sediments and rock layers found from that time. These include tropical carbonate platforms, reefs built by ancient sponge-like creatures called archosaurs, layers of bauxite, which forms in warm and rainy climates, and minerals such as evaporites and calcretes that form in dry areas. The wide spread of these features, especially in tropical regions across many latitudes, shows that Earth was in what scientists call a greenhouse climate, a time with no large ice sheets and steady high temperatures across much of the planet. Toward the end of the Cambrian, fossil evidence from trilobites, extinct sea creatures with hard shells, suggests there was only a small temperature difference between the poles and the equator. In other words, even the polar areas were not extremely cold, showing how evenly warm the planet was. Some scientists have found signs of ancient glaciers in the Avalonia region, which was located in high southern latitudes at the time. However, there is still debate about whether those icy sediments formed during the Cambrian or in the slightly earlier Neoproterozoic period. When it comes to measuring how hot the Earth really was during the Cambrian, the results are different depending on the method used. Some estimates suggest that the global average temperature may have been over 40 degrees Celsius. However, more dependable models that gather information from several sources give more moderate temperatures, around 20 to 22 degrees Celsius at the very beginning of the Cambrian, rising to about 23 to 25 degrees Celsius for the rest of the period. This long-lasting warmth was closely linked to high levels of carbon dioxide in the atmosphere. A major reason for this was the formation of the massive supercontinent Gondwana. As land masses moved together, Earth's tectonic plates shifted and created new edges where volcanic activity took place. These volcanic eruptions released large amounts of heat-trapping gases like carbon dioxide, which further warmed the planet. In particular, a huge volcanic event known as the Calcaringi, large igneous province, erupted around stage 4 of the Cambrian and continued into the early Meolingian. These eruptions released enormous amounts of carbon dioxide, methane and sulfur dioxide into the air, causing sudden climate changes and raising sea surface temperatures greatly. However, there is still a lot of doubt about exactly how hot the oceans became. Scientists try to understand this by studying oxygen isotope levels in ancient sea rocks, but there is ongoing disagreement about what those values really mean when comparing Cambrian oceans to other times in Earth's history. Depending on which estimates you consider, tropical sea surface temperatures during the Cambrian may have ranged from 28 to 32 degrees Celsius, or even from 29 to 38 degrees Celsius. By comparison, today's average tropical sea surface temperature is around 26 degrees Celsius. While temperatures rose quickly, oxygen levels in the air were still quite low compared to today. Oxygen had been increasing slowly since the Neoproterozoic period, thanks to the growth of organisms in the oceans that use sunlight to make food. But during the Cambrian, oxygen levels in the air went up and down between about 3% and 14%, far below the modern level of about 21%. The combination of low oxygen in the air and high ocean temperatures meant that less oxygen could enter seawater, especially in deeper areas. This led to oxygen-poor conditions, but during the Cambrian, oxygen levels in the air went up and down between about 3% and 14%, far below the modern level of about 21%. The combination of low oxygen in the air and high ocean temperatures meant that less oxygen could enter seawater, especially in deeper areas. This led to oxygen-poor conditions, where deep parts of the ocean were almost completely without oxygen. These low-oxygen environments had a strong effect on sea life and the growth of early animals. As new types of organisms began to dig into ocean sediments, they stirred up the layers of mud and exposed deeper, oxygen-poor material to the oxygen-rich water above. This process, known as bioturbation, actually reduced the burial of organic carbon and sulfur in the sediments. Over time, this made it harder for oxygen to increase in the air and oceans, leading to more widespread oxygen shortages underwater. On the other hand, when the continents experienced high rates of weathering, the breaking down of rocks due to wind, rain, and other natural forces, more nutrients flowed into the oceans. This sudden increase in nutrients led to a fast growth of phytoplankton, tiny organisms that use sunlight to make food and form the base of the food chain. Their rapid growth helped support the development of more complex animal life. But when these plankton blooms happened too quickly, they caused eutrophication, a process where too much organic matter is produced and later breaks down, using up oxygen and leaving waters seriously low in it. These cycles of rising and falling oxygen levels shaped life on Earth in powerful ways. Whenever oxygen levels increased, the variety of life increased. More oxygen supported more active ways of living, larger body sizes, and more complex ecosystems as oxygen-rich conditions spread across the sea floor. But when oxygen levels dropped, because of changes in sea level, shifts in ocean currents, or the rising of deeper oxygen-poor waters, many animals could not survive. These low oxygen events led to mass die-offs, sometimes in certain regions and other times across the world. The Ordovician period was an interesting part of Earth's ancient history. It was the second period of the Paleozoic era and also the second of 12 main periods that make up the Phanerozoic eon, the long stretch of time that includes most of Earth's complex life. The Ordovician lasted for about 41.6 million years, starting around 486 million years ago, right after the Cambrian period ended, and ending around 443 million years ago when the Silurian period began. The name Ordovician comes from the Ordovices, a Celtic tribe that once lived in what is now Wales. The period was officially named in the year 1879 by a British geologist named Charles Lapworth. At the time, there was a disagreement between two other geologists, Adam Sedgwick and Roderick Murchison, over which period certain rocks in northern Wales belonged to. Sedgwick said they were from the Cambrian, while Murchison said they were from the Silurian. But Lapworth noticed something important. The fossils in those rocks were different from both the Cambrian and the Silurian. So he suggested a completely new period, the Ordovician, to end the disagreement. It was not until the year 1960, about 40 years after Lapworth had died, that the International Geological Congress officially accepted the Ordovician as an official geologic period. During the Ordovician, life in the oceans didn't just survive, it grew strongly. The great burst of life that began during the Cambrian continued strongly. The oceans were full of invertebrates, especially mollusks and arthropods. Arthropods were especially important during this time, and some of them may have even started moving onto land, though they would not fully live there until the Devonian period, which came later. This period also saw the very first land plants, small and simple, but a clear sign of important changes ahead. One of the most exciting developments was the Great Ordovician biodiversification event, a time when the variety of life forms greatly increased. It was also during the Ordovician that fish, the world's first true vertebrates, began to develop, and there is evidence that fish with jaws may have first appeared toward the end of this period. Something very unusual also happened in the sky. During the Ordovician, Earth was struck by about 100 times more meteorites per year than we experience today. This strange event is called the Ordovician meteor event, and some scientists believe it may have been caused by a ring system that briefly formed around the Earth. The climate of the early Ordovician was extremely hot. Earth was in a greenhouse state, with sea surface temperatures as high as those during the early Eocene climatic optimum, a much later warm period. At the beginning of the Ordovician, the atmosphere had very high levels of carbon dioxide, but then things began to change. By the later part of the early Ordovician, the planet started to cool, moving into a milder phase during the Middle Ordovician. Eventually, the Earth entered a long, cold phase known as the Early Paleozoic Ice Age. This cold time may have started as early as the Florian Age, or perhaps a little later, during the Darwinian or Sanbian stages. During the Dapingian and Sanbian, there were also times of heavy rain, as shown by metal traces found in ancient rocks in the area now called Baltuscandia. Then, during the early Cartian, temperatures rose again for a short time in an event called the Boda event, which led to the formation of reef-like structures and the quick spread of sea life across what is now Europe. Another rainy phase also happened during the early Cartian. After that, Earth cooled again, and this finally led to a major ice age called the Hernantian glaciation, which happened at the very end of the Ordovician. During this time, sea levels were higher than at any other time in the Paleozoic era. The continents were mostly low and flat, so huge areas were covered by shallow seas. These shallow waters encouraged the growth of many kinds of sea creatures, especially those that built hard shells or skeletons from calcium carbonate. In the early Ordovician, sea levels kept rising and stayed high through the middle of the period. Although there were some local drops in sea level, the overall pattern stayed upward into the early late Ordovician. Then, as the Earth became colder in the few million years leading up to the Hernantian glaciation, sea levels began to fall steadily. During the Ice Age itself, sea levels rose and fell many times, but the exact details are still not completely clear. Some scientists think sea levels began changing even before the Hernantian glaciation officially started, but clear proof of glaciers does not appear until the very end of the period. There is now proof that glaciers formed during the Hernantian on what are now Africa and South America, which were located near the South Pole at that time. These southern lands helped form the icy caps of the Ice Age. Much like North America and Europe, the huge southern continent, called Gondwana, was mostly covered by shallow seas during the Ordovician. These warm, sunny waters were perfect for life that needed space to grow and build reefs or shells. The enormous Panthalassic Ocean stretched across most of the northern hemisphere, while several other ancient seas and oceans also existed, including Prototethys, Paleotethys, the Canti Ocean, which later disappeared by the end of the period, the Iapetus Ocean, and a newly forming sea called the Reich Ocean. During most of the late Ordovician period, life in the oceans was growing strongly. Many kinds of sea animals were doing well, and ecosystems continued to grow more detailed and connected. But as the period came to an end, something dramatic happened. A series of major extinction events struck. wiping out many creatures that had once filled the seas. Tiny tooth-like animals called conodonts and floating organisms like graptolites were badly affected. 2 entire groups of trilobites, Agnostida and Ptychoparida, disappeared completely, while another group called the Asaphida was reduced to only a small number. Other sea animals such as brachiopods, which looked like clams, bryozoans, which formed coral-like groups, and echinoderms, relatives of starfish and sea urchins, were also seriously affected. A type of squid-like creature known as the endocerid cephalopod was almost entirely wiped out, surviving only as rare forms in the next period, the Silurian. Scientists believe that this massive die-off may have been caused by a sudden ice age at the end of the Ordovician. This cooling may have been triggered by the spread of the first land plants, which changed Earth's climate by removing carbon dioxide from the atmosphere. The final part of the Ordovician became one of the coldest times in the last 600 million years of Earth's history. Despite the extinctions, the Ordovician period produced a wide range of new sea life that would shape the rest of the Paleozoic era. The oceans were filled with layers of animals that filtered tiny bits of food from the water. These animals formed simple food chains and lived in closely connected groups. Life during the Ordovician was far more varied and detailed than in the earlier Cambrian period, and this pattern of ocean life has continued, in many ways, up to today. One of the most amazing events of this time is called the Great Ordovician Biodiversification Event. It may not be as well known as the Cambrian explosion, but it was just as important. During this time, the number of sea animal groups increased 4 times, making up about 12% of all known sea life in the Phanerozoic eon. Many animals also became smaller than their Cambrian ancestors, and filter-feeding organisms became more common than ever before. By now, the older sea life from the Cambrian, like simple-shelled brachiopods, archaeocyathids, eocrinoids, and early trilobites, was being replaced. Taking their place were hinged brachiopods, crinoids, sea lilies, and many kinds of cephalopods, relatives of modern squids and octopuses. Hinged brachiopods especially began to spread across the ocean shelves, replacing trilobites in many areas. These changes showed a big rise in animals that made hard, shell-like coverings from calcium-rich minerals. The positions of the continents during the Ordovician also strongly affected what kinds of animals developed. Different regions formed their own special types of spineless sea life. For example, the continents of Laurentia and Baltica, which were near the tropics and surrounded by shallow, warm seas, had their own kinds of trilobites, different from those in Gondwana. Gondwana itself had separate animal groups in its warmer and cooler areas. Parts of Central Asia, like the Tian Shan region, were closely connected to Gondwana in terms of life forms. The Alborz region of what is now Iran also shared links with South China. Southeast Asia's sea life had strong connections to Gondwana too. North China shared similarities with both Laurentia and parts of South America that belonged to Gondwana. There was even a special group of animals living in what scientists call the Celtic province. However, some animals, such as the tropical hinged brachiopods, lived all around the world and were not limited to one area. As the Middle Ordovician began, sea animals spread more widely across the globe. Because of this, sea life became less regional and more shared between different areas, especially as oceans like the Iapetus Ocean became smaller. Even so, differences in sea life between regions continued until the end of the Ordovician. Trilobites, those armoured sea creatures with jointed legs and many eyes, were especially common and varied. They changed quickly during the Ordovician and developed many unusual features. Some grew long spines and bumps to protect themselves from hunters like early sea scorpions and meat-eating cephalopods. One trilobite called Eglina prisca even learned how to swim. Others developed wide front parts for digging through ocean mud. A group known as the trinucleids had strange, flat, pitted edges around their head shields. Some trilobites like Asaphus kowalewski grew long eye stalks to help them spot danger from far away, while others lost their eyes completely. By the end of the Ordovician, early relatives of spiders and scorpions may have started moving onto land. Although single coral animals had existed since at least the Cambrian, large reef-building corals appeared during the early Ordovician, along with the first known soft-bodied octocorals. This rise in coral reefs also meant more animals were using calcium to build shells and skeletons. Brachiopods became extremely varied, adjusting to almost every sea environment, from shallow coasts to deeper waters. Even after the great increase in life forms, they continued to change and grow quickly. Mollusks, which first appeared during the Cambrian, or perhaps even earlier in the Ediacaran, also became more common and came in many shapes and sizes. These included clams, snails, and straight-shelled cephalopods called nautiloids, which spread from shallow tropical seas to nearly all parts of the ocean. Graptolites, tiny colonial animals that floated in the sea, thrived throughout this period. A certain group called Nemergraptus gracilis became widespread during a time of very high sea levels in the Cambrian age. New types of crinoids and cystoids also appeared. Scientists once believed that the first true fish appeared in the Ordovician, but fossil finds from China now show that jawless fish likely already existed in the early Cambrian. The very first jawed fish may have begun to appear during the late Ordovician. Tiny flask-shaped microscopic fossils called chitinozoans, which first appeared in the late Woolluan age, went through a huge increase in number in the early Ordovician, known as the Tremodocian, quickly spreading around the world. Several animals during this time also formed close partnerships called symbiosis, where different species lived together and helped each other. At the start of the Ordovician, trilobites were joined by many new kinds of sea creatures. These included tabulate corals, many new kinds of brachiopods such as strophominids and rhinchonellids, branching bryozoans, floating graptolites, conodonts, and many kinds of mollusks and spiny-skinned animals. This group even included the first brittle stars and true starfish. Arthropods, the group that includes insects and crustaceans, remained common. Older trilobite groups from the Cambrian continued to exist, and a new group called Phacopida appeared. The earliest signs of land plants also showed up during the Ordovician, marking the start of a major change in Earth's living systems. In the middle of the Ordovician, ocean communities began to change. Trilobites became less dominant, and sea ecosystems became more balanced and varied. Brachiopods, bryozoans, mollusks, and spiny-skinned animals thrived. Corals became more varied, with tabulate corals spreading widely and the first horn-shaped rugose corals appearing. Floating graptolites continued to change and diversify, and a new group called Diplograptina appeared. One of the earliest known armored jawless fish, called Atrondaspes, lived during this time. The Middle Ordovician also saw a big rise in animals that drilled into hard materials like shells and rocks. This period is known as the Ordovician bioerosion revolution. Scientists know this because of the sudden appearance of many drilling trace fossils, with names like Tripanites, Paleocebella, Petroxestes, and Osprionides. The wearing away of hard surfaces by living things became an important force, especially in thick-shelled animals like corals, bryozoans, and brachiopods, and in the wide, hard seafloors made of calcium-rich rock that were common then. During the later part of the Cambrian period, and even more during the Ordovician that followed, green algae were already quite widespread. These green algae are believed to be the ancestors of the first land plants. Sometime in the middle to late Ordovician, more than 460 million years ago, tiny, soft plants that looked like modern liverworts began to grow on land. These early plants did not have special tubes to carry water and nutrients through their bodies like most modern plants do. Fossil spores found in Ordovician rocks are similar to those of bryophytes, a group that includes mosses and liverworts today. Along with the first land plants, some of the earliest fungi were also beginning to grow well. Among them were special fungi known as arbuscular mycorrhizae, part of a group called the glomerales. These fungi formed an important partnership with early plants by attaching to their roots. In return for sugar from the plants, the fungi helped collect minerals from the soil and pass them into the plant's cells. This teamwork, called mycorrhizal symbiosis, was very important in helping plants survive on land. Fossils of these fungi, including their thin thread-like structures and tiny spores, have been found in Ordovician rocks from what is now the United States state of Wisconsin. These fossils are about 460 million years old, from a time when land was mostly empty except for simple, moss-like plants and these helpful fungi. Meanwhile, in the oceans, strange layered structures called stromatolites, formed by layers of tiny living organisms, mostly bacteria, were still present, although they were far less common than they had been during the Proterozoic eon, billions of years earlier. By the Ordovician, stromatolites were found only in certain separate places. The Ordovician period ended in a dramatic way. A series of extinction events swept through the oceans and destroyed a huge number of living things. Altogether, these disasters form the second largest mass extinction in Earth's entire history. Only the much later Permian Triassic extinction was worse. These terrible extinctions happened between 447 million and 444 million years ago, right at the boundary between the Ordovician and the next period, the Silurian. The Silurian period was an important chapter in Earth's history. It lasted for about 23.5 million years, beginning at the end of the Ordovician period around 443 million years ago, and ending at the start of the Devonian period about 420 million years ago. This period was the third out of 6 main periods in the Paleozoic era, and the third of 12 periods in what scientists call the Phanerozoic eon, the time when visible, complex life grew and spread across Earth. Even though geologists have clearly marked the rock layers that show the beginning and end of the Silurian, the exact timing is still not certain by a few million years. The Silurian began right after a terrible worldwide event, one of the biggest mass extinctions in Earth's oceans. During this crisis, around 60% of sea species disappeared. It marked a dramatic turning point and a fresh start for life on our planet. One of the most exciting things about the Silurian was that life began to spread onto the land in a serious way. This major step is often called the Silurian-Devonian land revolution. Before this time, most life lived underwater, but now plants and animals were beginning to adapt to life on dry ground. Early land plants that had no roots or water-carrying systems slowly changed into vascular plants, which could move water and nutrients inside their bodies and grow taller. Alongside them, new kinds of fungi, especially Dicarian fungi and glomeromycotan fungi, spread and became more varied, helping plants develop root systems and survive in rocky, harsh places. At the same time, 3 important groups of arthropods, myriapods, like millipedes, arachnids, like spiders, and hexapods, insects and their relatives, became fully suited to life on land. This was the first wave of animals to permanently leave the ocean behind. The Silurian also saw a rapid increase in the variety of jawed fish. New groups such as placoderms, armoured fish, acanthodians, which would later give rise to modern sharks and rays, and osteichthyans, bony fish, appeared. The bony fish later divided into two types: lobe-finned fish, which would eventually lead to amphibians and humans, and ray-finned fish, which fill the seas today. However, as these jawed fish grew and spread, the older jawless fish like ostracoderms and conodonts began to decrease in number. The balance of power in the ocean was changing. The Silurian period was first named and described in the early 1830s by a Scottish geologist named Roderick Murchison. He studied fossil-rich rock layers in southern Wales and chose to name the period after the Silures, an ancient Celtic tribe that once lived in the area. This name was inspired by his friend and fellow geologist Adam Sedgwick, who had earlier named the Cambrian period after another Latin name for Wales. However, Murchison's identification of Silurian rocks in some places overlapped with rocks that Sedgwick had assigned to the Cambrian. This caused a serious scientific disagreement that ended their friendship. Later, an English geologist named Charles Lapworth solved the problem by creating a new period between the Cambrian and Silurian, which he called the Ordovician. In other regions, some scientists used a different name for the Silurian, Gotlandian, after rocks on the island of Gotland in the Baltic Sea. The French geologist Joachim Barrande, building on Murchison's work, divided Silurian rocks in Bohemia, now part of the Czech Republic, into 8 stages, though later research showed that some of these actually belonged to the Devonian period. Even so, his work made Bohemia one of the most important places for studying early Silurian fossils. During the Silurian, the ancient supercontinent Gondwana lay across the equator and stretched over much of the southern half of the Earth. At the same time, a vast ocean covered the northern half of the globe. Because sea levels were very high and most land was low and flat, many small islands formed, creating many different environments where life could grow and thrive. Gondwana continued to move slowly southward, but the ice sheets from the previous period's ice age began to melt. This caused sea levels to rise. In many places, Silurian rock layers sit directly on top of worn-down Ordovician rocks, showing geologists that the seas flooded back over the land. At the same time, the continents Avalonia, Baltica, and Laurentia were drifting toward the equator and eventually crashed into each other. This was the beginning of a new supercontinent called Euramerica. When early Europe collided with North America, it pressed and folded layers of ancient sediments that had built up over millions of years. This powerful earth-shaping event is known as the Caledonian Mountain Building event, which affected a huge area from present-day New York State across Greenland, through Europe, and all the way to Norway. As the Silurian came to an end, sea levels fell again. This drop left behind salty basins, evaporate deposits, stretching from Michigan to West Virginia. The newly formed mountain ranges also began to wear down quickly. One ancient river, the Tees River, cut into older Ordovician rocks and left behind Silurian sediments in what is now northern Ohio and Indiana. In the northern half of the Earth, the enormous ocean called Panthalassa dominated the planet. Other seas and oceans included 2 early forms of the Tethys Ocean, the Prototethys and the Paleotethys, as well as the Rhyic Ocean, the Iapetus Ocean, a narrow sea between Avalonia and Laurentia, and the newly formed Ural Ocean. The Silurian period was once thought to have been a time of calm and steady warmth. This was compared to the icy extremes of the Ordovician period before it, and the intense heat that followed in the Devonian period. But today scientists know that the Silurian climate was far from steady. In fact, the planet experienced many dramatic climate changes during this time. We know this because of major changes seen in carbon and oxygen isotopes, chemical signs left behind in rocks from that age. Sea levels also changed greatly during the Silurian. At the beginning of the period, they rose sharply from their low point during the Hernantian Ice Age, then slowly fell again toward the end. However, this was not a simple rise and fall. Sea levels moved up and down in smaller cycles as well. Scientists have identified 15 clear, high sea level periods, when the ocean rose above the edges of the continents. At its highest, the Silurian sea level was likely about 140 meters, or 459 feet, higher than its lowest point. During the Silurian, Earth entered a warm greenhouse phase. The atmosphere contained large amounts of carbon dioxide, about 4,500 parts per million, much higher than today's levels. Warm, shallow seas spread across the tropical parts of the planet. In the early Silurian, glaciers that had once extended into the continents shrank and slowly moved back towards the South Pole, nearly disappearing by the middle of the period. The climate of this time was also marked by strong and frequent storms. We know this from thick layers of coquina, rocks made of broken shells that were formed by storm-driven waves hitting the seafloor. The Silurian climate and carbon cycle were surprisingly unstable, showing more frequent changes than in any other geological period. Scientists have named several of these dramatic events, such as the Ordovician event, the Mulder event, and the Lau event. Each was marked by a small extinction, sudden sea level shifts, and sharp changes in carbon isotope levels. Creatures living freely in open waters, like plankton, were especially affected. Brachiopods, corals, and trilobites also suffered. These extinction events often happened quickly, in short bursts. Some researchers think these changes were caused by repeated ice ages, but because there are few clear ice deposits, like tillites, from the middle to late Silurian, this idea is still debated. Paleontologists see the Silurian as a time when life was still healing from the late Ordovician mass extinction, a huge event that had interrupted the steady growth of biodiversity that began in the Cambrian and continued through most of the Ordovician. But the Silurian was not only about recovery, it was also a time of exciting new beginnings. For the first time in Earth's history, large fossils of land life appeared. These included small moss-like plants growing along lakes and streams, forming the first simple forests. There were also large fungus-like organisms known as nematophytes, which lived in networks and likely had close links with underground fungi. This was the beginning of the Silurian-Devonian land revolution, when life slowly began to take over the land. However, these early land organisms did not yet have a major effect on the planet. That would happen later in the Devonian. The Devonian period is one of the most interesting chapters in Earth's long and dramatic story. It belongs to the Paleozoic era, which is part of the Phanerozoic eon, the great stretch of time when visible life became common. The Devonian lasted for about 60.3 million years, beginning roughly 419 million years ago at the end of the Silurian period, and ending around 359 million years ago when the Carboniferous period began. It is the fourth geological period of both the Paleozoic and the Phanerozoic. The name Devonian comes from the county of Devon in southwestern England, where rocks from this ancient time were first carefully studied. During the Devonian, the surface of the Earth went through amazing changes, especially on land. Life that had mostly stayed in the oceans was now beginning to spread across the continents. Plants that could release spores into the air, called free-sporing vascular plants like ferns, began spreading far and wide. Over time, they formed thick, rich forests, covering much of the land in deep green. By the middle of the Devonian, many plant species had developed real roots and wide leaves, and near the end of the period, the first plants that produced seeds, called seed ferns, appeared. This major change of life on land is part of what scientists call the Silurian-Devonian land revolution. This was not just a quiet spread of simple plants, it was a slow but powerful change that reshaped the air, the soil, and the entire surface of Earth. Along with the rise of plants, the first land-living animals also began to appear. These early creatures were mostly arthropods, animals without backbones that had jointed legs and hard outer shells. The pioneers included creatures like millipedes, spiders, and early insects, which likely began their move onto land as early as the Ordovician period. Meanwhile, beneath the waves, the oceans were filled with life, especially fishes, which increased greatly in variety and number. Because of this rich life in the seas, the Devonian is often called the Age of Fishes. One group of fish, known as placoderms, had thick armoured plates covering their bodies, and they ruled many ocean environments. At the same time, cartilaginous fishes like early sharks became more common than they had been during the Silurian and late Ordovician periods. A special group of fish called tetrapodomorphs also began to develop in Devonian freshwater habitats. These were the ancestors of all four-limbed animals, including frogs, reptiles, birds, and even humans. Their strong, fleshy fins slowly began changing into legs and feet, though they were not yet ready to walk on land. That step would come much later, in the late Carboniferous period. The Devonian also saw the arrival of the very first ammonites, relatives of modern squids and octopuses, with spiral shells and tentacles. At the same time, older sea creatures such as trilobites, brachiopods, and wide coral reefs were still doing well, at least for a time. Around 375 million years ago, a destructive mass extinction struck the oceans. Many of the great reef systems collapsed. Jawless fish and placoderms were almost completely wiped out, and most trilobites disappeared, except for a small group called the Proetida. Another extinction event followed soon after, at about 359 million years ago, destroying even more sea life, including calcite sponge reefs and the last of the placoderms. These two disasters nearly ended the age of fishes and deeply shook Earth's ecosystems. The Carboniferous period was an important chapter in Earth's long story. It was part of the Paleozoic era and lasted for about 60 million years, starting around 359 million years ago, at the end of the Devonian period, and ending roughly 299 million years ago, marking the start of the Permian period. This period was the fifth of six main parts within the Paleozoic era, and also the fifth period in the larger timeline called the Phanerozoic Eon. In North America, geologists often split the Carboniferous into two smaller time sections, the Mississippian, earlier, and the Pennsylvanian, later. During the Carboniferous, life on land had become firmly established. Animals with backbones and four limbs, called tetrapods, were doing very well. These animals had come from lobe-finned fish during the Devonian, and by the Carboniferous had grown 5 fingers or toes on each limb, a feature called pentadactylus. Because amphibians were so common and spread widely during this time, the Carboniferous is often called the Age of Amphibians. One large group of amphibians, called temnospondyls, became the main animals on land. Even more important was the first appearance of amniotes, a new group of land animals that laid eggs on land. This group split into two main branches: synapsids, which would later develop into mammals, and sauropsids, the ancestors of today's reptiles and birds. At the same time, land-living arthropods like arachnids, such as giant scorpions and spider-like creatures, myriapods, like the huge millipede-like Arthropleura, and especially insects, including the first flying ones, went through a rapid increase in new types and variety. Tall forests filled with giant ferns, seed ferns and club mosses covered the land, growing in vast swampy areas. Over millions of years, the remains of these thick forests were buried and slowly changed into deep layers of coal, which is why this period is called the Carboniferous, a name that means coal-bearing. In the later part of the Carboniferous, the Earth went through a time of cooling, and glaciers formed in parts of the southern half of the planet. Sea levels fell and the continents slowly moved together to form a huge supercontinent called Pangaea. Near the end of the period, a small extinction event happened, known as the Carboniferous rainforest collapse. This event, caused by climate change, led to the disappearance of many rainforests and the extinction of several species. For a long time, scientists thought that the amount of oxygen in the air during the Carboniferous was always very high, much higher than today. But more recent studies suggest that oxygen levels actually changed over time. They began low but later rose sharply, at times reaching as high as 25 to 30%, compared to about 21% today. This high oxygen level may have allowed some insects and arthropods to grow to very large sizes. The idea of arranging Earth's rock layers into a time system began in the late 18th century. The name Carboniferous was first used in 1799 by the Irish geologist Richard Kirwan. Later, in 1811, it appeared in print as part of a heading by John Furey Sr., Coal Measures or Carboniferous Strata. 4 main rock layers were first included in the Carboniferous: Old Red Sandstone, Carboniferous Limestone, Millstone Grit, and the Coal Measures. In 1822, geologists William Conybeare and William Phillips officially grouped these layers into a Carboniferous unit. Then, in 1835, Phillips named it the Carboniferous system. Later, scientists realized that the Old Red Sandstone actually belonged to the older Devonian period. Because rock layers in the British Isles were very similar to those in Western Europe, scientists created a shared European system. The Carboniferous was divided into 2 main parts: the Lower Dinantian, mostly made of limestone, and the Upper Silesian, mainly made of sandstone and shale. The Dinantian was further split into the Tournasian and Visaean stages. The Silesian was divided into the Namurian, Westphalian, and Stephanian stages. In North America, geologists saw a similar pattern, but chose to divide the Carboniferous into 2 separate systems: the Mississippian, rich in limestone, and the Pennsylvanian, rich in coal and shale. These 2 divisions were officially recognized in 1953 by the United States Geological Survey. In Russia, geologists in the 1840s divided the Carboniferous into lower, middle, and upper sections, using rock layers from Russia. By the 1890s, these sections were named Dinantian, Muscovian, and Uralian. The Serpukhovian stage was added to the lower Carboniferous, while the Muscovian and Gzhilian formed the upper part. Later, the Bashkirian stage was added in 1934. In 1975, the International Commission on Stratigraphy officially standardized the Carboniferous timescale. They kept the Mississippian and Pennsylvanian from North America, the Tournasian and Visaean from Western Europe, and the Serpukhovian, Bashkirian, Muscovian, Kasimovian, and Gzhilian from Russian geology. This made earlier terms like Dinantian and Silesian mostly outdated. though some are still used in Europe today. To help geologists around the world agree on time periods, the International Commission on Stratigraphy uses a method called the Global Boundary Stratotype Section and Point. This means choosing a specific rock layer at a certain place to mark the start of a stage. So far, the Carboniferous system and only 3 of its stages have officially defined boundaries of this kind, because the rocks and fossils can be complex and hard to match worldwide. The name Mississippian was first suggested by Alexander Winchell in 1870, based on rock layers seen along the upper Mississippi River. During this time, a shallow sea connected the Paleo-Tethys Ocean with the vast Panthalassic Ocean, allowing sea animals to spread across the world. This made it easier to match rock layers by using fossils. However, there are very few volcanic rocks from the Mississippian, so dating these rocks exactly is hard. The Tournaisian stage, named after the city of Tournai in Belgium, was introduced by André Dumont in 1832. The boundary marking the start of this stage and of the entire Carboniferous period is found in southern France, at a place called La Serre. Scientists first defined this boundary based on the appearance of a fossil called Siphonodella sulcata, but later studies showed problems with this method, making it difficult to match the exact timing worldwide. The Viséan stage, also named by Dumont in 1832, is named after the town of Visé in Belgium. Its boundary point is now placed in southern China, based on the appearance of a fossil called Eoparostaphylla simplex, a type of tiny shelled animal. This decision was made in 2009. The Serpukovian stage was first suggested in 1890 by Sergei Nikitin and named after the city of Serpukhov near Moscow. It still does not have an officially chosen boundary point. The boundary between the Viséan and Serpukovian stages matches a time of major climate cooling and the spread of glaciers. This caused sea levels to fall and separated many sea habitats, which made species develop differently in different places, making it harder for scientists to match rock layers worldwide. Researchers are still working in places like the Ural Mountains and southern China to find the best place for defining this boundary, possibly using the first appearance of a fossil called Lochria ziegleri. The Bashkirian stage is the first stage of the Pennsylvanian period. It was suggested in 1934 by a Russian geologist named Sofia Semikhatova. She named it after Bashkiria, the old name for the region now called the Republic of Bashkortostan, in the southern Ural Mountains of Russia. The official start of the Pennsylvanian and the Bashkirian is marked by the appearance of a tiny fossil called the Conodont Declinognathodus noduliferus. This boundary is recorded at a place called Arrow Canyon in Nevada, United States, and was officially recognized in 1996. Back then, Arrow Canyon was part of a warm, shallow tropical sea stretching from southern California to Alaska. The rock layers there show a repeating pattern called a cyclothem, made of alternating shallow marine limestones and set sandstones, followed by mudstones and broken-up limestones, showing the rise and fall of ancient sea levels. The Moscovian stage is named after marine limestones and colorful clays found near Moscow, Russia. This stage was introduced in the year 1890 by geologist Sergei Nikitin. Unfortunately, this stage still does not have an officially defined starting point, called a GSSP, Global Boundary Stratotype Section and Point. In the northern and eastern parts of Pangaea, a tiny single-celled fossil, called Aljutovella aljutovica, could mark the start of this stage, where, however, because it is only found in certain areas, it is not useful for comparisons worldwide. Other possible markers include the first appearance of conodonts, like Declinognathodus donetzianus or Idiognathoides postsulcatus. Places in the Ural Mountains and in Nashui, in Guizhou Province, southwestern China, are being considered to define this boundary. The Casimovian is the first stage of the Upper Pennsylvanian. It was named after the city of Kasimov in Russia and was first part of Nikitin's Moscovian stage. Later, in the year 1926, A.P. Ivanov recognized it as a separate stage and called it the Tigoliferina Horizon, based on a type of fossilized brachiopod. The start of the Casimovian happened when global sea levels were very low, leaving gaps in rock layers from that time. This makes it hard to find fossil species useful for comparisons worldwide. Like the Moscovian, the Casimovian still does not have an official GSSP. Possible places include the southern Ural Mountains, the southwestern United States, and Nashui in China. The Gzhelian is the last stage of the Pennsylvanian. It is named after the village of Gzhel, near Ramenskoye, in the Moscow region. Once again, Sergei Nikitin defined it back in 1890. This stage also does not have a GSSP. Fossils of fusulinids like Rauserites rossicus and Rauserites stuckenbergi are useful for dating rocks in areas like the Boreal Sea and the Paleotethyan region, but they are not found in eastern Pangaea or near the edges of the huge Panthalassa Ocean. Scientists are thinking about sites in the Urals and Guizhou, China, to define this stage more exactly. The change from the Pennsylvanian to the Permian period is marked by a GSSP in the Idaralash River Valley near the city of Aktauba, Kazakhstan. This boundary, officially agreed on in 1996, is marked by the first appearance of a fossil conodont called Streptognathodus postfusus. A cyclothem is a repeating pattern of rock layers made of both marine, formed under the sea, and non-marine, formed on land, sediments. Each cyclothem shows a single cycle of sediment, starting with an eroded surface at the bottom. Though each one may be only a few meters thick, when stacked together they can form sequences that are hundreds or even thousands of meters thick. Cyclothems formed along continental shelves, which were very shallow and flat. This meant that even a small change in sea level could move the shoreline a lot, either flooding land or exposing large areas to erosion. The main time for cyclothem formation was during the late Paleozoic Ice Age, which lasted from the late Mississippian to the early Permian periods. As glaciers grew, they pulled water from the oceans, causing sea levels to drop. Rivers then cut channels into the exposed land, and plant roots broke down rocks to form soils. These layers of non-marine sediments formed the base of each cyclothem. When glaciers melted, sea levels rose quickly. Wet lowlands turned into peat swamps, and thick layers of plant matter built up in these low-oxygen areas. Over time, this plant matter turned into coal. As the seas rose, they flooded these peatlands, adding sediments from deltas, lagoons, and estuaries. Eventually, fully marine conditions returned, covering everything with limestone, followed by deep-water black shales as sea levels reached their highest point. Although sea levels fell again later, the process was slower and often eroded older layers instead of building new ones. Because the rise in sea level was so fast, the resulting sediment layers were usually less than 10 meters thick. During the Pennsylvanian, cyclothems were common in shallow tropical seas that covered parts of Laurussia, a region that included what is now the western and central United States, Europe, Russia, and Central Asia, as well as parts of the North and South China, cratons. These repeating sea level changes followed the glacial cycles of the late Paleozoic Ice Age. The Permian period was an important chapter in Earth's ancient history. It lasted for about 47 million years, starting at the end of the Carboniferous period, around 298,900,000 years ago, and ending at the start of the Triassic period. about 251,900,000 years ago. The Permian was the sixth and last period of the Paleozoic era, after which came the Mesozoic era, starting with the Triassic. The name Permian was first used in the year 1841 by the British geologist Sir Roderick Impey Murchison. He named it after the region of Perm in Russia, where he found clear layers of rock during his geological studies near the Ural Mountains, together with French geologist Edouard de Verneuil. In that area, Murchison noticed a huge stack of different rocks, like marl, limestone, schist, sandstone and conglomerate, sitting on top of older Carboniferous rocks. These new layers were different from anything seen before, and that's how the Permian became officially recognized as a new geological period. The name of the region itself, Perm, comes from an old medieval kingdom called Permia, which once occupied the same land, and is now part of today's Perm Krai in Russia. Before the term Permian was used, geologists in Germany called these rocks Rotliegend and Zechstein, while in Britain they were thought of as part of the new red sandstone. During the Permian period, the Earth looked very different. All the continents had come together to form one huge supercontinent called Pangaea. This enormous landmass was created when Euramerica and Gondwana crashed into each other during the Carboniferous. It was surrounded by a giant ocean called Panthalassa. Inside Pangaea, the climate became hotter and drier, especially after the Carboniferous rainforests died out, leaving behind large deserts. As the environment became harsher, animals had to adjust. Amphibians, which needed water to live and reproduce, started to decline. In their place rose a new group of animals called amniotes, creatures that laid eggs with protective shells, which made them better suited for dry areas. These amniotes eventually split into two main groups: the synapsids, which include the ancestors of mammals, and the sauropsids, which include reptiles and eventually birds. The Permian period also saw several waves of extinction, at least 3 and maybe 4, according to scientists. One major extinction happened at the end of the early Permian, during a time called the Silurian epoch. During this event, many early synapsids, especially a group often called pelycosaurs, died out, and more advanced forms known as therapsids started to appear. Later, during the Capetanian stage, near the end of the Middle Permian, another big extinction event took place. This was probably linked to massive volcanic eruptions in what is now China, forming the Emetian Traps. But the worst disaster was still ahead. At the very end of the Permian, around 251 million years ago, the world went through the worst mass extinction in Earth's whole history. This event, called the Permian Triassic extinction, or sometimes the Great Dying, wiped out about 81% of marine species and 70% of land species. It was a truly devastating global disaster. The cause is strongly linked to huge volcanic eruptions in Siberia, which formed the Siberian Traps, vast layers of lava and ash that released massive amounts of poisonous gases and carbon dioxide, causing the climate to collapse. Life took a very long time to recover. On land, ecosystems needed 30 million years into the Triassic period to fully rebuild. The naming of the Permian was not without arguments. A French-American geologist named Jules Marcoux, between 1853 and 1867, found Permian-age rocks across a large part of North America, from the Mississippi River to the Colorado River. He suggested calling it the Diassic period, a mix of Dias and Trias, but Murchison strongly opposed this name, and it was never widely accepted. For many years afterward, the United States Geological Survey refused to recognize the Permian as a separate period. Until the year 1941, they treated it as part of the Carboniferous period, grouping it with other subdivisions called the Mississippian and the Pennsylvanian. To organize the Permian more clearly, geologists divide it into three main time blocks, called epochs, from oldest to youngest: Ciceralian epoch, Guadalupian epoch, and Lopingian epoch. Each epoch is further divided into smaller slices of time called stages, which match rock layers from different places in the world. These stages also help scientists line up the timing of rock layers across continents. To make this global coordination accurate, the International Commission on Stratigraphy, ICS, uses something called a Global Boundary Stratotype Section and Point, GSSP. This is a specific place, usually a rock formation, that marks the start of a stage and is used as the official reference for geologists worldwide. For most of the 20th century, geologists only split the Permian into two parts, early and late Permian, with the Cambrian stage considered the last stage of the early Permian. But in the year 1992, geologist Glenister and his team suggested that the stages called Rhodian to Capitanian were different enough to be their own middle epoch. This idea was officially accepted in 1999, and since then the three-part division has been the standard way to describe the Permian. In the past, scientists studying Permian ocean rocks mostly used fossils of ammonoids, spiral-shelled marine animals related to modern squids and octopuses. But these fossils are not very common in Permian rocks, and each ammonoid species often lived for many millions of years, which makes it harder to use them to mark specific times. Because of this, experts now use the fossil remains of a different kind of ancient creature, conodonts, to define key time boundaries in the Permian. Conodonts were mysterious, eel-like animals without jaws that had tiny, tooth-like structures in their mouths. Although they are long extinct, their hard mouthparts fossilized well and are found in many rock layers from the Paleozoic era and the Triassic period, making them very useful for identifying and comparing rock layers worldwide. The official starting points for each age of the Permian, called GSSPs, Global Boundary Stratotype Section and Point, are now based on the first appearance of certain species of conodonts in the fossil record. The Ciceralian series, which is the earliest part of the Permian, gets its name from rocks found on the western slopes of the Ural Mountains in what is now Russia and Kazakhstan. The term Ciceralian was suggested in the year 1982 by geologist J.B. Waterhouse. At first it included three stages, the Aselian, Sakmarian and Artinskian, but later the Kungurian stage was also added to match the Russian classification of the Lower Permian. Earlier in the year 1900, French geologist Albert-Auguste Cochon de Lapparent had suggested the name Uralian series, but it was later dropped because it was not used consistently. The Aselian stage was named in the year 1954 by Russian geologist V.E. Ruzhenchev, after the Asel River in the southern Ural Mountains. The official GSSP for the start of the Aselian is located in the Ider-Alash River Valley, near Aktobe in Kazakhstan. This boundary was officially accepted in the year 1996, and it is defined by the first appearance of a conodont species called Streptognathodus postfusus. Next is the Sakmarian stage, which gets its name from the Sakmara River, also in the southern Urals. This name was introduced by the famous Russian geologist Alexander Karpinsky in the year 1874. The GSSP for the start of the Sakmarian is found at a site called the Usolka section in the same region, and this boundary was officially approved in the year 2018. It is marked by the first appearance of the conodont species Suetognathus binodosus. The Artinskian stage is named after the town of Arty in the Sverdlovsk region of Russia. Like the Sackmarian, it was named by Karpinski in the year 1874. Currently, there is no officially agreed upon GSSP for the start of the Artinskian, but scientists have suggested defining it by the first appearance of a conodont species known as Suetognathus affinis whitei. The Kungurian stage is named after the city of Kungur in the region of Perm Krai. It was introduced by Alexander Antonovich Stukenberg in the year 1890. Like the Artinskian, it still does not have an officially approved GSSP. However, some recent studies suggest marking its beginning by the first appearance of the conodont species Neostreptognathodus pnevi. Moving to the middle part of the Permian, we have the Guadalupian series, named after the Guadalupe Mountains in the states of Texas and New Mexico in the United States. This name was first used in the year 1902 by American paleontologist George Herbert Gertie, based on the thick layers of marine rocks found in that region. The first stage of the Guadalupian is the Rhodian, named in the year 1968 after the Rhode Canyon member of the Word Formation in Texas. The GSSP for the start of the Rhodian is located in the Stratotype Canyon in the Guadalupe Mountains, about 42 meters 7 centimeters above the base of the Cutoff Formation. This GSSP was approved in the year 2001, and it is marked by the first appearance of the conodont species Gynogondolilla nankingensis. The second stage is the Wardian, named after the word formation. It was first used in a formal way in 1961 by geologists Glenister and Furnish, though the original name was created earlier in 1916 by Johann August Uden. The GSSP for the Wardian is located in Guadalupe Pass, Texas, in a rock layer called the Getaway Limestone member of the Cherry Canyon Formation. This GSSP was also officially accepted in 2001, and its base is marked by the first appearance of Gynogondolella acerata, another kind of conodont. The final stage of the Guadalupian is the Capitanian, named after the Capitan Reef in the Guadalupe Mountains. The name was first given by George Burr Richardson in 1904, and it was later formally used as a substation by Glenister and Furnish in 1961. The Capitanian was officially recognized as an international stage by the International Commission on Stratigraphy in 2001. Its GSSP is located at Nipple Hill in the southeastern part of the Guadalupe Mountains. The start of the Capitanian is marked by the first appearance of the conodont species Gynogondolella postserrata. The term Lopingian was first used in 1923 by a geologist named Amadeus William Grabau, who called it the Loping series, after the town of Leping in Jiangxi Province, China. At first it was used just to describe a certain type of rock layer, what scientists call a rock unit. But in 1932 another Chinese geologist, T.K. Huang, made its use broader. He made the Lopingian a more official level in geology, calling it a series that included all the rock layers from the Permian period in South China that lay above a limestone layer called the Maoku limestone. Many years later, in 1995, the Subcommission on Permian Stratigraphy, which is part of the International Commission on Stratigraphy, officially voted to recognize the Lopingian as a worldwide standard in geological time, what is known as a time-based rock unit. Within the Lopingian series, there are two main stages, the Wuxiapingian and the Changxingian. These names were first suggested in 1962 by the geologist J.Z. Sheng. He introduced them as part of the Wuxiaping Formation and Changxing Formation, both found in the Lopingian rock layers. The official boundary marking the start of the Wuxiapingian stage was set in 2004. It is based on a location called Penglaitan in Guangxi, China. This boundary is marked by the very first appearance of a tiny tooth-like fossil from an extinct eel-like creature called Clarkina postbeteri, which belonged to a mysterious group of jawless animals called conodonts. The Changxingian stage, on the other hand, got its name from the Changxing limestone, a rock layer first described by Grabau back in 1923. This limestone is named after Changxing County in Zhejiang province. The boundary that marks the start of the Changxingian is about 88 centimeters above the bottom of the Changxing limestone, in a place called Meishan Section D in Zhejiang. This boundary was officially accepted in 2005 and is marked by the first appearance of another conodont species called Clarkina wangi. To mark the change from the Permian period to the Triassic period, scientists chose a point at the bottom of a rock layer called Bed 27C, also in the Meishan D section. This point was accepted as the official boundary in 2001 and is marked by the first appearance of yet another conodont fossil, called Hindiotus parvus. In Russia, the usual geological timescale includes a stage called the Tartarian, which covers the entire Lopingian period as well as the earlier Capitanian and part of the Wordian stages. The stage below that, called the Kazanian, includes the rest of the Wordian and the even earlier Roadian stage. Meanwhile, in North America, geologists divide the Permian into different stages. The earliest is the Wolfcampian, which itself includes two smaller stages, the Neelian and the Lennoxian. Then comes the Leonardian, which includes the Hessian and Cathedralian stages. After that is the Guadalupian, followed by the Ochoan, which roughly matches the Lopingian used in other parts of the world. In New Zealand, geologists have made their own time scale for the Permian period. They divide it into three major periods: the pre-Telfordian period, which is not divided further and roughly matches the Aselian, Sakmarian and Artinskian stages; the D'Urville period, which is divided into the Makarian, Waitian and Puruhawan stages, and roughly equals the Kungurian stage and the Guadalupian period; and the Aparima period, which includes the Fletian, Barretian, Mangapirian and Telfordian stages and matches closely with the Lopingian period. During the Permian period, all of Earth's main landmasses had joined together to form a single giant supercontinent called Pangaea. To the east of Pangaea were smaller land fragments called the Carthasia terranes. This huge landmass stretched from near the equator all the way toward the poles, strongly affecting global climate and ocean currents. Around this supercontinent was a huge ocean called Panthalassa, meaning universal sea, and a smaller ocean called the Paleotethys, located between Asia and the southern landmass called Gondwana. During this time, a smaller continent named Cimmeria broke away from Gondwana and began drifting north toward Laurasia, shrinking the Paleotethys Ocean. Meanwhile, a new ocean called the Neotethys was starting to form in the south. This Neotethys Ocean would later become a major ocean during the Mesozoic era. As the massive Panthalassa Ocean pushed under the southeastern edge of South China, a volcanic chain called a magmatic arc began to form. This chain stretched all the way to the island of Hainan. The central Pangaean mountains had started forming back in the Carboniferous period, when the continents of Laurasia and Gondwana collided. These mountains reached their tallest height during the early part of the Permian, around 295 million years ago, and were thought to be as high as the modern Himalayas. However, over time, they were worn down by weathering and erosion. Elsewhere, a landmass called the Kazakhstania Block collided with Baltica during the early Permian, also called the Ciceralian Epoch. By the end of the Permian, several regions, including the North China Craton, the South China Block, and Indochina, had all joined together and become part of Pangaea. In what is now northwestern Europe, a salty inland sea called the Zechstein Sea existed. This sea had extremely salty conditions and is called a hypersaline epicontinental sea. Because the inside of such a huge continent like Pangaea was far from the ocean, it had extreme temperatures, hot summers and freezing winters. These conditions also caused seasonal rain and dry periods, similar to modern monsoons. Deserts were widespread across Pangaea. These dry conditions helped the rise of gymnosperms, a group of seed-bearing plants like conifers, cycads, and ginkgos, which can survive dry conditions better than plants like ferns, which need moisture to reproduce. In fact, the first modern-style trees appeared during this time. Some of the most important places in the world for Permian rocks are the Ural Mountains in Russia, where the name Permian comes from, regions of China, and the southwestern United States, especially Texas, where bright red rock layers called the Texas red beds are found. The Permian Basin, which stretches across Texas and New Mexico, is named for its deep layers of Permian rocks. It has some of the thickest Permian deposits on Earth. During the very beginning of the Permian, called the Aselian stage, sea levels dropped slightly. They then stayed relatively high, several tens of meters above today's sea level, through much of the early Permian. But starting in the Rhodian stage, sea levels began to fall sharply. This drop reached its lowest point during the Wuchia-Pingian, when sea levels dropped to almost the same as today. After that, in the Changxingian, sea levels began to rise again slightly. At the start of the Permian, the Earth was still in an ice age that had started long ago in the late Devonian period, more than 360 million years ago, and had continued through the whole Carboniferous period. This icy period reached its coldest point in the late Pennsylvanian epoch, which was part of the Carboniferous. As the Permian began, the climate slowly started to change. In the Silurian epoch, which marks the early part of the Permian, the planet began to dry out. This drying was especially noticeable in regions near the equator, particularly across Pangaea, the giant supercontinent that covered most of the world. At the same time, the melting of ancient ice sheets caused sea levels to rise. Around the boundary between the Carboniferous and Permian periods, a short warming event happened. Although temperatures rose, the climate also became much drier, and these dry conditions continued. However, during the Aselian and Sacmarian stages, both in the early Permian, the Earth cooled again, reaching the peak of the Ice Age. Then, by about 287 million years ago, something dramatic happened. The Artinskian warming event began, and the climate became warmer once more. The great ice cap over the South Pole started to shrink, but some glaciers still remained on the highlands of eastern Australia, northern Siberia, and southern Africa. This warming also caused even drier conditions, especially in the middle of the continents. Later, near the end of the Kungurian stage, the Earth cooled again, starting a new ice period that lasted into the early Capetanian stage. Even though it was cooler, the average temperatures were still warmer than they had been at the very start of the Permian. Yet another cool phase came during the Middle Capetanian, lasting about 3 to 4 million years. This was called the Kimura event. But this cool period did not last long. Around 260 million years ago, a huge volcanic eruption happened in what is now southwestern China, forming the Imatian Traps. The gases and heat from this eruption caused a sudden warming called the Imatian Thermal Excursion, which helped lead to a mass extinction in the Capetanian. As the Wuchia-Pingian stage in the late Permian began, the leftover volcanic rocks from the Imatian Traps started reacting with carbon dioxide in the air, removing it from the atmosphere and causing global temperatures to drop again. By the late Wuchia-Pingian, the long-lasting late Paleozoic Ice Age finally ended, and the last glaciers in Australia melted away. Then came the most dramatic climate event of all, the end of the Permian. At the boundary between the Permian and Triassic periods, a massive volcanic eruption took place in Siberia, creating the Siberian Traps. This eruption released more than 5 million billion tons of carbon dioxide into the air, more than twice the amount that had been there before. This sudden release of greenhouse gases caused a huge warming, shown by a sharp drop in oxygen isotopes in ancient rocks. The result was devastating: the Permian-Triassic mass extinction, the largest extinction in Earth's history. Nearly all forms of life were affected, and the Earth entered an intense, hot period that lasted for millions of years into the Triassic period. During the Permian, the climate was extremely seasonal. A special type of weather system called a megamonsoon formed because of Pangaea's huge landmass and its position on the planet. These massive seasonal winds caused extreme dryness in the inside regions of the supercontinent, while places along the western shores of the ancient Paleo-Tethys Ocean received very heavy rainfall. Scientists have found many pieces of evidence for this megamonsoon. For example, signs of ancient rainforests have been discovered in the Changtang Basin of Tibet, and rock layers in Australia's Sydney Basin show big seasonal changes in sediments, burrows, and fossils. Climate models using modern weather patterns also show that such a strong monsoon system would naturally develop under the conditions of the Permian Earth. The increasing dryness near the equator, especially during the Ciceralian, was probably caused by the strengthening of this global monsoon. The oceans of the Permian were full of life. There were many types of mollusks, brachiopods, and echinoderms, like sea stars and sea urchins. Brachiopods were especially common and varied, and one group called the Productida made up about half of all known brachiopod groups from this time. These animals even helped shape reef environments as ecosystem builders. Among the shelled sea creatures called ammonoids, the Goniatitida were common in the early and middle parts of the Permian, but they began to fade later. Another group, the Prolecanitida, were never very varied. A new group called the Ceratitida evolved from the Prolecanitida during the middle of the Permian and grew rapidly toward the end of the period. As for trilobites, only 3 families were still around during the Permian: Proetidae, Brachymetopidae, and Philipsidae. They did not change much early on, but they had one last burst of variety during the Kungurian to Wardian stages. By the final stage of the Permian, the Changxingian, only about 4 to 6 trilobite groups remained. Corals were also declining during the middle and late Permian. On land, the Permian had a wide variety of plants, fungi, arthropods, and 4-legged vertebrates called tetrapods. Much of Pangaea was covered in huge dry deserts, especially in the northern hemisphere. The heat was so strong that many rocks formed during this time turned reddish from iron oxides, as the sun baked the bare, plantless land. At the start of the Permian, plants still looked a lot like they had in the Carboniferous. But around the middle of the period, big changes began. Swamp-loving lycopod trees like Lepidodendron and Sigillaria started to disappear. In their place came more advanced seed ferns and the first conifers, especially in the dry inland areas. This change happened after the collapse of the Carboniferous rainforests. By the end of the Permian, those ancient swamp plants survived only on a chain of tropical islands called Cathasia, which lay near the equator in what would later become South China. Meanwhile, conifer trees grew in many different types. These included the ancestors of many modern tree families. In the southern parts of the world, huge forests of seed ferns, known as the Glossopteris flora, thrived. Oxygen levels may have been quite high there. ginkgo trees and cycads, which are still around today, also appeared during this fascinating chapter of Earth's history. During the Permian period, which lasted from about 299 million years ago to around 252 million years ago, insects, tiny creatures that had already become quite common in the earlier Carboniferous period, went through a big increase in variety. In the early Permian, many new types of insects appeared and they began to evolve in many directions. But by the time the Permian was ending, things slowed down. Both the speed at which new insects were evolving and the speed at which older ones disappeared dropped a lot. By the start of the Permian, something interesting was already happening. A kind of evolutionary arms race between insects and plants. Insects had started to feed on plants in more complex ways, and plants in turn were developing defenses, features that helped protect their reproductive parts from insect damage. Fossils show signs of insect bites on ancient plant leaves, and we also find plants with tough outer layers and spikes to keep insects away. Among the most common insects at this time were early versions of groups called Paleoptera, Polyneoptera, and Paraneoptera. One major group that had dominated in the Carboniferous, the Paleodictyopteroidea, began to disappear. This was likely because they were facing strong competition from a new group called the Hemiptera, which had similar piercing-sucking mouthparts and lived in similar ways. Another old group, the Meganisoptera, which included the largest flying insects ever known, giant relatives of dragonflies, also started to decline during the Permian. At the same time, a very important group of insects called the Holometabula began to spread and form many different types. These are the insects that go through complete metamorphosis and include today's beetles, flies, butterflies, and bees. Another group called the Grilloblattidans, now extinct, reached their peak during the Permian period. In some places they made up about 1/3 of all insect types. These unusual insects are thought to be distant relatives of modern ice crawlers. Scorpion flies, known as Mecopterans, first appeared in the early Permian and became quite varied by the late Permian. Some of them, like members of the Mesocycidae family, had long tube-like mouth parts, which suggest they may have pollinated ancient seed plants called gymnosperms. The first beetles also appeared at the start of the Permian. These early beetles, such as those from the Permoscupidae family, likely ate rotting wood. Later, some beetle groups even adapted to live in water by the end of the Permian. By this time, members of modern beetle groups like Archostomata, Adephaga, and possibly even Polyphaga had already evolved, the last being the most varied beetle group alive today. When it comes to land fossils from the Permian, the record is somewhat incomplete. Fossils from the early Permian mostly come from tropical areas in Europe and North America. But for the middle and late Permian, we rely mostly on rocks from cooler areas like South Africa's Karoo Basin and the Ural Mountains in Russia. In the early Permian, land animals in North America and Europe were mostly primitive mammal-like reptiles called synapsids, especially plant-eating edaphosaurids and meat-eating sphenocodontids. Alongside them lived diadectids, early reptile-like creatures, and many amphibians. Small insect-eating reptiles like the Aclistorhinids were also common at this time. The synapsids, which are the ancestors of mammals, became more successful and varied during the Cisuralian epoch, the early part of the Permian. One famous member of this group was Dimetrodon, a predator with a large sail on its back. However, around the time between the Cisuralian and the next epoch, the Guadalupian, things began to change. Amphibians declined, and the older types of synapsids, the pelycosaurs, were gradually replaced by more advanced ones called therapsids. This change wasn't sudden. it took about 20 million years, from the Cambrian stage to the end of the Cambrian. As predators and prey evolved, their interactions became more active and complicated. But due to gaps in the fossil record, especially during the transition from the Silurian to the Guadalupian, scientists struggle to figure out exactly how these changes happened. Some experts have identified a period called Olson's Gap, which may show a worldwide shortage in fossil deposits. Others suggest that North American and Russian records overlap more than previously thought, and some propose there was even an extinction event during this time, what's been called Olson's extinction. In the Middle Permian, animal life in South Africa and Russia was dominated by therapsids, especially a varied group called the dinocephalians. These creatures went extinct at the end of the Middle Permian during the Carboniferous mass extinction. In the late Permian, the land was ruled by more advanced therapsids, like the saber-toothed gorgonopsians and the plant-eating dicynodonts with turtle-like beaks. Large parareptiles called pariasaurs also roamed the land. Another group of reptiles, the archosauromorphs, distant ancestors of crocodiles, dinosaurs, and flying pterosaurs, first appeared and began evolving in the late Permian. Archosauriforms, a subgroup of archosauromorphs, made their first appearance right at the very end of the Permian. Cynodonts, which are the direct ancestors of all mammals, also appeared and spread around the world in the late Permian. Another therapsid group called therocephalians, like Lycosuchus, appeared during the Middle Permian. Though there were no flying vertebrates yet, some reptiles, such as those from the Vigeltisauridae family, had wing-like structures that allowed them to glide through the air. These gliding lizards are the earliest known vertebrates able to glide. During this time, ancient amphibians known as temnospondyls reached their peak in the early Permian, the Silurian, but many disappeared in the middle to late Permian, especially after Olson's extinction. Another group, the embolomeres, crocodile-like creatures that lived in water, were thought to have disappeared earlier, but have now been found in late Permian rocks in China. In the field of paleontology, the Triassic period is a very important part of Earth's geological history. It lasted for about 50 million years, starting around 252 million years ago, right after the huge end of the Permian period, and ending about 201 million years ago when the Jurassic period began. This period is the first and shortest part of the Mesozoic era, often called the Age of Reptiles, and is also the seventh period of the Phanerozoic Eon, the long stretch of time that includes all visible life. The Triassic was framed by two huge mass die-offs, one at the start and one at the end, both of which had a big effect on life on Earth. The Triassic is split into three main parts, or epochs: the early Triassic, the middle Triassic, and the late Triassic. The story of the Triassic begins after one of the greatest life disasters the planet has ever faced, the Permian Triassic extinction event, which wiped out most life on Earth. But from this destruction, new life started to appear and change in surprising ways. Fossils from the Triassic show us three main groups of creatures: survivors of the Permian die-off, who were tough and adaptable, short-lived species that lived for a while during the Triassic and then disappeared, and long-term winners like dinosaurs and early mammals, who would go on to shape life for millions of years. During this time, reptiles, especially a group called archosaurs, ruled the land. Among these, archosaurs were the ancestors of crocodiles, birds, and dinosaurs. Though dinosaurs appeared in the late Triassic, they were not yet the main rulers they would become in the Jurassic. Instead, the Triassic world was mostly ruled by pseudosuchians, crocodile-like archosaurs that came in many different shapes and sizes. Some archosaurs even took to the skies, becoming the very first flying backboned animals, the pterosaurs with leathery wings stretched between long fingers. Before the archosaurs took over, the therapsids, mammal-like reptiles, had been the top land animals during the Permian. In the Triassic, some of them, such as dicynodonts and cynodonts, made a brief comeback. But they slowly declined, and most disappeared by the end of the period. Yet from the cynodonts came a remarkable new group, the early mammals, or mammaliamorphs. These small, shrew-like creatures were smart and adaptable, and although they stayed in the shadows, they survived and would thrive in the next era. Amphibians also had their time in the Triassic. Giant, semi-water predators called temnospondyls survived the end Permian crisis and spread again. But like many others, they eventually went extinct. Meanwhile, the first members of today's amphibian families, early frogs, salamanders, and caecilians, started to appear and survive the next great extinction. In the water, fish called neopterygians, including the ancestors of modern bony fish, appeared early in the Triassic and spread quickly. They soon became important players in both rivers and oceans. During the Triassic, Earth's continents were still joined together in one giant supercontinent called Pangaea. This huge landmass stretched almost from pole to pole and was surrounded by a vast ocean. Because of its massive size, the center of Pangaea was far from the cooling effect of the sea. As a result, its climate had extreme seasons, with very hot summers and very cold winters. Most of the land was dry and desert-like, especially in the center, where red sandstones and salt deposits called evaporates formed. Interestingly, while the center was dry, the polar regions were not frozen. Instead, they were wet and mild, with forests and even reptiles. There were no glaciers anywhere on Earth during this time. The huge size of Pangaea also caused strong cross-equator winds, giant weather systems so strong they are sometimes called Pangaean megamonsoons. These storms swept from one side of the supercontinent to the other. Though the Triassic was mostly dry, shorter wet periods came and went, especially in tropical areas near the Tethys Sea. Fossils and layers of sediment from places like the Svalbard Islands, North America, South China, and Argentina show that these humid times happened several times. The strongest of these periods was the Carnian pluvial event, a big increase in rainfall and humidity that happened during the Carnian stage of the late Triassic. It may have caused changes in ecosystems around the world. The early Triassic was one of the hottest times in all of Earth's history. This heat was caused by the massive release of greenhouse gases from volcanic eruptions in an area called the Siberian Traps. This time began with the Permian Triassic thermal maximum, then cooled slightly during the Diurnarian cooling between about 251 and 249 million years ago, before heating up again during the latest Smithian thermal maximum around 249 to 248 million years ago. After that came another short cooling called the latest Olenekian cooling, when temperatures dropped by about 6 degrees Celsius. The Middle Triassic was cooler overall, though it had a warm period near the end of the Anisian stage. A longer cool period, called the Ladinian-Carnian cooling, lasted from about 242 to 233 million years ago. At the start of the Carnian, global temperatures stayed mild, but around 234 million years ago, volcanoes in the Wrangellia, large igneous province, erupted, sending heat into the air and causing the Carnian pluvial event. This led to a warm and wet phase called the Mid-Carnian warm interval, which lasted until about 227 million years ago. After that, the early Nourian cool interval brought another chill from 227 to 217 million years ago, followed by the Mid-Norean warm interval, which lasted until about 209 million years ago. A brief cold spell may have happened around 214 million years ago, possibly due to the Manicouagan meteor impact. By about 212 million years ago, changes in Earth's orbit caused wetlands to expand and dry areas to shrink. Then came the Ratian cool interval, which lasted from 209 to 201 million years ago. At the very end of the Triassic, Earth experienced another extreme heat wave called the End Triassic Thermal Event. This was caused by huge volcanic eruptions from the Central Atlantic Magmatic Province, which released massive amounts of carbon dioxide into the air. The result was the Triassic-Jurassic extinction event, another huge life crisis that allowed dinosaurs to finally take over in the Jurassic period. After the greatest extinction in Earth's history, the Permian Triassic extinction, life started to recover during the Triassic period, which began around 252 million years ago. But the world was not the same. It was hotter, drier, and full of strange new landscapes. Many living things that survived the extinction now had to adjust to a very different planet. At the very start of the Triassic, a group of ancient spore-producing plants, called lycophytes, became very common, especially those from a group called isoetyles, which includes modern quillworts. The most famous among them was a plant called Pleuromeia, which grew tall and straight like a green column, sometimes reaching up to 2 meters high, about the height of a grown man. These plants thrived in the unstable environment after the extinction, but as the climate slowly became more stable in the Middle Triassic, they began to fade away. A new kind of seed plant called Bennettitales, which first appeared during the Permian, started to spread widely across Earth during the late Triassic and became an important part of Mesozoic plant life. In the southern continents that were once part of the giant landmass Gondwana, forests were often dominated by a strange tree called Dicroidium, a kind of extinct seed fern from the group Corystospermales. It was especially common during the Middle to Late Triassic. Meanwhile, ginkgos, a group of plants that now has only one living member, a ginkgo biloba, started to spread and diversify. Triassic forests were also full of conifers, which included extinct groups like Voltziales and a family called Chirolepidiaceae, which first appeared in the late Triassic and would later become common through the rest of the Mesozoic era. Interestingly, scientists have found no coal deposits from the very start of the Triassic. This mysterious gap in coal formation is called the Early Triassic Coal Gap, and it seems to be another result of the mass extinction. Ideas for this include falling sea levels, acid rain from huge volcanic eruptions in Siberia, global warming that dried out swamps, or the extinction of swamp plants with a long wait before new species evolved to replace them. There might have even been a sharp drop in oxygen in the soil, making it hard for peat, the first stage of coal, to form. In the oceans, a new group of corals began to grow, although the reefs they made were small compared to the huge coral reefs seen today or in the ancient Devonian period. Around the end of the Carnian Age in what is now South China, these coral communities went through a sudden crisis. Other sea creatures also appeared or did well during this time. Serpulid worms showed up in the Middle Triassic, and a group of tube-building animals called microconchids were everywhere. One of the great success stories of the oceans was the return of ammonites, shelled relatives of squid and octopuses, which bounced back from near extinction and began to thrive again. Bivalves, the group that includes clams and mussels, also started to spread rapidly during the Middle Triassic and became one of the main animals in the seas. In freshwater habitats, insects began to change into many new forms. This was especially important for a group called Holometabula, which includes most of the insect species we know today, such as beetles, flies, butterflies, and bees. In the oceans, rivers, and lakes, fish populations began to recover in a big way. After the extinction, fish species were similar all around the world, what scientists call a widespread distribution. One ancient group of fish called coelacanths, thought to be almost extinct, actually had their highest variety after the Devonian and were doing quite well in the early Triassic. The group we know today as ray-finned fishes or actinopterygians also had a big increase in variety during the Triassic, especially in the middle part of the period. However, scientists still don't fully understand how this happened, partly because some fossils were not well preserved. Among the newcomers were the first members of the teleosts, which today are the most varied group of fishes. Some ray-finned fish like saurichthyids and bergeriids were fierce hunters, growing longer than 1 meter and 20 centimeters, that's over 3 feet. In freshwater lakes and rivers, lungfish like Ceratodus were common, mostly known from their strong tooth plates. Another group, the hybodonts, were shark-like creatures that lived in both fresh and salt water throughout the Triassic. One strange group of ancient cartilaginous fish, called eugeneodontids, survived for a short time into the early Triassic before disappearing forever. A group of ancient amphibians, called temnospondyls, survived the extinction and lived on during the Triassic. The land-dwelling types mostly died out, but the water-dwelling ones lived on. Early species like Tupilactosaurus, Thabanquea, and Micropholis disappeared in the early Triassic, but others like the Stereospondyli did very well, and some even survived until the Cretaceous period. The largest among them, like Mastodonsaurus, could grow between 4 and 6 meters long, more than 13 to 20 feet. At this time, the first modern amphibians, called lissamphibians, also appeared. The ancestors of today's frogs had already shown up by the early Triassic, but these creatures didn't become common until the Jurassic, after the temnospondyls had mostly disappeared. The reptiliomorphs, a group of early backboned animals that were close relatives of the first reptiles, almost completely disappeared during the Triassic. Only 2 water-loving groups survived, the Embolomeri, which vanished early on, and the Chroniosuchians, which survived until the end of the period, but after the extinction, a new group of reptiles rose to dominate, the archosauromorphs. These reptiles had already begun to evolve during the Permian, but the disaster gave them room to grow in variety. Among them were the proterosaurs, long-necked, lizard-like creatures. The most famous was Tanystropheus, which had a neck longer than the rest of its body. Another family, the Charovipterigidae, had long back legs they may have used for gliding. Other archosauromorphs like rhynchosaurs and allocotosaurs were plant-eaters. Rhynchosaurs had big barrel-shaped bodies and beaked mouths with rows of teeth and were very common during the middle part of the Triassic, but died out around 220 million years ago. Allocotosaurs included animals like Trilophosaurus, with 3 cusped teeth, Pteroterpiton, with a long snout, and the horned Shringosaurus, which was around 3 to 4 meters long, nearly 10 to 13 feet. One important group of archosauromorphs was the archosauriforms, which were fierce hunters with sharp teeth and legs placed directly under their bodies for faster movement. Early in the Triassic, big-headed hunters like the erythrosuchids were top predators. Later on, the phytosaurs became widespread. They looked a lot like crocodiles and probably lived in the same way, waiting in water to catch fish and reptiles. But this was a case of convergent evolution. They just looked similar but were not closely related. True archosaurs, the group that would later lead to dinosaurs, birds and crocodiles, split into 2 main branches early in the Triassic, Avermetatarsalia, the bird line, and Pseudosuchia, the crocodile line. At first, the birdline archosaurs were not very important in ecosystems, but by the late Triassic, they had given rise to pterosaurs, the first flying reptiles, and dinosaurs. The first dinosaurs appeared during the Carnian age and included small meat-eaters like Coelophysis, which was about 1 to 2 meters long. Early plant-eating dinosaurs called sauropodomorphs mainly lived in cooler areas. One mysterious large predator from this time, known as smog, might have been an early dinosaur or a crocodile relative. It's still not clear. Meanwhile, the Pseudosuchians, the crocodile line, were the main animals on land. This group included armored plant-eaters called etosaurs, huge meat-eating reptiles called Rauisuchians, and the first small fast crocodilomorphs. The Rauisuchians were top predators of the Triassic and came in many forms, from giant four-legged hunters to slim two-legged ones with deep sails on their backs. After the Triassic ended, only the crocodilomorphs survived into the Jurassic and later times. During the Triassic period, the world's oceans were home to a wide variety of interesting marine reptiles. One major group was the Sauropterygians, which included animals like pachypleurosaurs and nothosaurs. These two types of reptiles were especially common during the Middle Triassic, especially in the warm tropical waters of the Tethys Ocean. This group also included placodonts, which had thick bodies and strong jaws for crushing shellfish, and a strange but important early plant-eating marine reptile called Atopodentatus, the earliest known plant-eating marine reptile. Later, the first plesiosaurs, famous for their long necks and paddle-like limbs, also evolved from this group. Around the same time, the seas also saw the rise of other marine reptiles, like the thalatosaurs, which had long lizard-like bodies. One early example was Ascleptosaurus. Another major group was the Ichthyopterygians, which looked a bit like modern dolphins. They first appeared in the oceans during the early Triassic, and soon after, they evolved into many different forms. By the Middle Triassic, some of these ichthyosaurs had grown to huge sizes, becoming some of the largest sea animals of their time. Back on land, the first turtles began to appear during the Nourian age of the late Triassic period, around 220 million years ago. Early turtles like Proganocheles and Proterocursus had already developed hard shells for protection. Another group of reptiles, called Lepidosauromorphs, which would later give rise to modern lizards and snakes, also began to appear during the Carnian age, a slightly earlier stage of the late Triassic. However, their ancestors probably existed even earlier, possibly as far back as the Permian period. There were also some unique and strange reptiles like the drepanosaurs. These small tree-living reptiles had bodies shaped like chameleons, beaks that looked like birds, and claws specially made for holding branches. Another group, the Procolophonids, were small lizard-like plant-eaters. They were the last surviving members of an older branch of reptiles called the parareptiles, and they continued to play an important role in their habitats until the end of the Triassic. Meanwhile, three groups of therapsids, reptile-like ancestors of mammals, managed to survive into the Triassic. These were the Dicynodonts, the Therocephalians, and the Cynodonts. The Cynodont Cynognathus, for example, was a fierce hunter and was common in parts of the southern continents, Gondwana, during the Olenekian and Anisian ages of the early and middle Triassic. Among the plant-eaters, the Canamaeriform Dicynodonts and the Gomphodont Cynodonts were especially important, grazing across the Triassic lands. The Therocephalians included both large meat-eaters like Moscorhinus and plant-eaters called borides, although they eventually died out halfway through the Triassic. In the late Triassic, another group of large, fast-moving meat-eating cynodonts called ectoninids appeared. And it was during the Carnian age, the early part of the late Triassic, that some advanced cynodonts changed into the first mammals, marking a big turning point in Earth's history. At the same time, another group of reptiles called archosaurs was rising to power. These included the ancestors of crocodiles, pterosaurs, and dinosaurs. They became the biggest and most successful land animals of the Triassic, pushing the therapsids into smaller roles in nature. This change, sometimes called the Triassic takeover, may have helped mammals evolve, as therapsids and their mammal-like descendants were forced to live in hiding, literally. They became smaller, more active at night, and ate insects. This likely led to the development of fur to stay warm and a faster metabolism to stay active in the dark. The Jurassic period was an important time in Earth's history. It started about 201 million years ago, after the Triassic period ended, and lasted until about 143 million years ago, when the Cretaceous period began. This period is the second and middle chapter of the Mesozoic era and the eighth geological period of the Phanerozoic Eon. It is named after the Jura Mountains, where scientists first found thick layers of limestone rocks that formed during this time. The Jurassic began after a huge extinction at the end of the Triassic. This disaster was probably caused by massive volcanic eruptions in a place called the Central Atlantic Magmatic Province, which released huge amounts of gas and lava. Another big event happened about 183 million years ago called the Torsion Oceanic Anoxic Event. During this time, the oceans lost a lot of oxygen, became more acidic, and Earth's temperatures rose quickly. These changes were probably caused by even more volcanic eruptions, this time from the Karoo-Ferrar volcanic areas in what is now southern Africa and Antarctica. By the start of the Jurassic, the huge supercontinent called Pangaea had begun splitting into two giant landmasses, Laurasia in the north and Gondwana in the south. The climate then was much warmer than today. There were no polar ice caps, and forests even grew near the poles. The Earth had vast dry areas near the equator and thick forests in many other regions. Life on land was changing fast. Dinosaurs, which had already appeared in the Triassic, now became the main land animals. They pushed aside other reptile groups and took over most environments. The first early birds evolved from small meat-eating dinosaurs. Other animals that first appeared in the Jurassic include the earliest frogs, salamanders, lizards, crabs, and mammals that looked like modern ones. Mammal ancestors, called Mammaliaformes, began to spread into different types. Reptiles, called crocodilomorphs, started moving from land into water. In the oceans, large marine reptiles like ichthyosaurs and plesiosaurs were common. Flying reptiles, called pterosaurs, ruled the skies. Modern groups of sharks and rays first appeared and began to spread out. A very important group of modern fish, called teleosts, also appeared near the end of this period. Plants during this time were mostly ferns and seed plants, especially conifers, many of which still exist today. A now extinct group called the Bennettitals was also common. The Jurassic climate was generally warm, about 5 to 10 degrees Celsius, hotter than today. Carbon dioxide levels were about 4 times higher than today. Even though Earth was warm overall, there were occasional cold snaps, especially in places like northeastern Siberia, where winters could be freezing. The deep oceans were also warmer, and coral reefs grew closer to the poles than they do now. Most deserts and dry lands were located in areas between 40 degrees north and south of the equator. Rainforests and tundra were rare, and ice sheets were probably not present, because summers were too warm for snow to build up. Some mountains may have had glaciers, though. The climate changed many times during the Jurassic. At the very beginning, Earth warmed suddenly after the Triassic extinction. Then there was a cooler period between 199 and 183 million years ago, called the Early Jurassic Cool Interval. Some scientists think there may have been small ice ages during this time. Then, about 183 million years ago, Earth heated up again during the Tortian warm interval, with some parts of the planet reaching 40 degrees Celsius or more. Oceans near the equator went over 30 degrees Celsius. After that came another cooler phase, the Middle Jurassic Cool Interval, between about 174 and 164 million years ago. Some short ice ages may have happened then. Later, around the Bajocian Age, Europe briefly became wetter before turning dry again. Another possible short ice age happened in the late Bajocian. One of the coldest times came at the Calovian-Oxfordian boundary, where Earth may have entered another ice age. Next came a warmer phase called the Kimmeridgian warm interval, from about 164 to 150 million years ago, possibly one of the wettest periods of the Jurassic. Earth's interior became less extreme in seasonal changes as the Atlantic Ocean began to open and added more moisture to the air. Near the end of the Jurassic, another cooling phase began, called the Early Tithonian Cooling Event, which led into the cooler Tithonian Early Barremian Cool Interval, lasting into the early Cretaceous. One of the most dramatic events in the Jurassic was the Tortian Oceanic Anoxic Event, TOAE. It happened in the early Tortian Age, about 183 million years ago, and involved a serious loss of oxygen in the oceans, global warming, and high carbon dioxide levels. It caused many sea creatures, especially shell-forming animals like brachiopods, to die out. Oddly, marine reptiles were barely affected. During the TOAE, a massive lake formed in the Sichuan Basin in what is now China. It may have been 3 times bigger than modern Lake Superior and trapped huge amounts of carbon. The oceans became more acidic, which stopped many tiny sea creatures from forming shells. Extra phosphorus in the water made the lack of oxygen worse, creating a cycle that made the low oxygen conditions even stronger. The end of the Jurassic was not marked by a clear mass extinction, but it was a time of big change. Some groups of animals grew in number while others declined. Dinosaurs, which had started to diversify in the late Triassic, became even more successful and widespread during the early Jurassic. Many new types of theropod dinosaurs appeared during this time, including the earliest relatives of T-Rex, such as Proceratosaurus, and strange forms like Limosaurus, a beaked dinosaur that lost its teeth and ate plants. Feathered dinosaurs, including early Scansoriopterygids with bat-like wings, also evolved. True birds appeared by the middle to late Jurassic, with Archaeopteryx from Germany being one of the earliest known examples. Among the plant-eating dinosaurs, early ornithischians like Lesothosaurus and Heterodontosaurids showed up in the early Jurassic. Later, ankylosaurs, stegosaurs, and other armored dinosaurs evolved. Some, like Culindadromeus from Russia, had feathers or feather-like coverings. The first horned dinosaurs, called ceratopsians, appeared in China. The biggest land animals ever, sauropods, reached enormous sizes during the Jurassic. Some were as heavy as 12 tons or more, like Ledumahadi from South Africa. Earlier, smaller two-legged relatives had mostly died out by the Middle Jurassic. Giant sauropods like Volcanodon, Cetiosaurus, and Mamenchisaurus dominated the land. By the late Jurassic, groups like Diplodocus and Brachiosaurus had spread across the world. The crocodile-like animals called pseudosuchians mostly went extinct at the end of the Triassic, except for crocodilomorphs, which survived and thrived. During the Jurassic, these animals took on many new shapes and ways of living. Some stayed on land, others became fully aquatic. One group called Thalattosuchians even developed flippers, tail fins and smooth skin like dolphins. Another group, the Neosuchians, were the ancestors of today's crocodiles and started living in fresh water. The oldest known Neosuchians might be Calcoiasuchus from Arizona, though its exact place in the family tree is still debated. Other ancient crocodile relatives like Razanandrongobi from Madagascar may have belonged to a mostly southern group called Notosuchia. The Cretaceous period was an amazing time in Earth's history. It began about 143 million years ago and ended around 66 million years ago. This period was the third and last part of the Mesozoic era, after the Triassic and Jurassic periods. Not only was it the final stage of the age of dinosaurs, but it was also the longest period in the whole Phanerozoic eon, lasting for about 77 million years. The name Cretaceous comes from the Latin word creta, meaning chalk. That's because a lot of chalky rock formed during this time, especially in the later part of the period. Today you can still see those old chalk layers in places like the White Cliffs of Dover in England. During the Cretaceous, Earth's climate was very warm, much warmer than it is today. There were no large ice caps at the poles, and sea levels were so high that wide, shallow seas flooded inland areas across many continents. These warm, shallow seas were full of strange and interesting creatures like ammonites, spiral-shelled animals, rudists, reef-building clams, and marine reptiles that are now extinct. On land, dinosaurs were still the rulers, coming in all shapes and sizes. Thick forests, full of plants, reached all the way to the polar regions. There were even short periods of cooler weather in the first half of the Cretaceous, which may have brought brief times of ice or snow. Many of the animals and plants we know today started in the Cretaceous. New types of mammals and birds began to appear, including the earliest relatives of placental and marsupial mammals, the groups that would eventually include animals like humans, kangaroos, and whales. Some of the first true birds also evolved during this time, growing feathers and the ability to fly in ways like modern birds. The sea saw the rise of teleost fish, a group that today includes everything from goldfish to tuna. During the Cretaceous, a very varied group within them, called the Acanthomorpha, started to do well. One of the most important events in the history of life happened during the Cretaceous: the rise of flowering plants, also called angiosperms. These plants, which now make up about 90% of all plant species, began to bloom and spread across the world. They started out small in the early Cretaceous but quickly spread, replacing the older, seed-producing gymnosperms like conifers, cycads, and ginkgos. By the end of the period, flowering plants had become the main type of plant life on Earth. The earliest known pollen grains from flowering plants, with just a single groove, have been found in rocks from about 134 million years ago in Israel and Italy. Later in the period, around 90 million years ago, some of the first large flowering trees grew as tall as 50 meters, or about 160 feet, with trunks nearly 2 meters wide. Grasses, which are part of the flowering plant family, also appeared during the Cretaceous, with the oldest fossils dating back to the Albian Age, about 110 million years ago. Ferns belonging to the group Polypodiales, which make up most modern ferns, also began to spread during this time. Although mammals were still mostly small in the Cretaceous, they were very important members of the ecosystem. In some areas, certain mammals called multituberculates were even more common than dinosaurs. These early mammals had many roles. Some were meat-eaters, others plant-eaters, and some even lived in the water. True marsupials and placental mammals appeared only near the very end of the Cretaceous, but their early relatives were already trying out different ways of living. Dinosaurs, of course, were still the top hunters on land, Many species evolved during this time, including the Maniraptora, a group that includes both birds and their closest dinosaur relatives like raptors, oviraptors, and therizinosaurs. Fossils from places like the Yixian Formation in China show amazing details, including feathers on many of these animals, giving a stunning view into ancient life. Flying reptiles called pterosaurs were very common in the early and middle parts of the Cretaceous, but their numbers began to drop towards the end. Only a few special families, Pteranodontidae, Nyctosauridae, and Azhdarchidae, survived until the last years. Insects also had a boom during this time. The earliest ants, termites, and butterflies appeared, along with aphids, grasshoppers, and gall wasps. Some other old animals started to disappear. Rhynchocephalians, relatives of today's tuatara, vanished from many areas, likely due to competition from more advanced lizards and mammals. However, they stayed common in some southern regions, especially in parts of South America, where they outnumbered lizards by a huge margin, 200 to 1 in some places. Another interesting group, the Choristoderes, freshwater reptiles that looked a bit like crocodiles, thrived in Asia during the early Cretaceous. Some had long necks, like the strange Hyphalosaurus, while others, such as the Neochoristodera, looked a lot like modern gharials. By the late Cretaceous, a type called Champsosaurus had spread across much of western North America. These creatures even reached the Arctic, thanks to the warm climate. Sadly, the Cretaceous period came to a dramatic end about 66 million years ago, when a massive asteroid crashed into what is now the Gulf of Mexico, leaving behind the huge Chicxulub crater. This impact triggered the Cretaceous-Paleogene extinction event, one of the most devastating mass extinctions in Earth's history. Non-bird dinosaurs, pterosaurs, large marine reptiles, and many other life forms disappeared almost overnight. This disaster marks the clear boundary between the Mesozoic era and the beginning of the Cenozoic era, the age of mammals and of flowering plants which still shape our world today. During the Cretaceous period, the oceans were full of life and many new sea creatures became common. This was the time when rays, modern sharks, and a group of advanced fish called teleosts were thriving in the seas. Several kinds of large marine reptiles also lived during this time. Ichthyosaurs, which looked a bit like dolphins, were common in the early and middle parts of the Cretaceous but disappeared during a major ocean event near the end of the period, known as the Cenomanian-Turonian anoxic event. Another group, the plesiosaurs, with their long necks and flipper-like limbs, lived throughout the entire Cretaceous. Later in the period, giant marine lizards called mosasaurs appeared and became the top hunters in the oceans. Sea turtles were also around during the Cretaceous. Two groups, Cheloniidae and Panchelonioidea, lived during this time and survived the mass extinction at the end of the period. Today, only one species from Panchelonioidea still exists, the leatherback sea turtle, the largest living sea turtle. There were also flightless marine birds called Hesperonithiformis that swam in the oceans like modern grebes, using their strong legs to dive and catch fish underwater. Among the many shelled creatures in the sea, one of the most noticeable was baculites, a type of ammonite with a long, straight shell. These creatures lived alongside reef-building clams called rudists, which played a major role in creating underwater reefs. Another important group of bivalves, called inoceramids, were very widespread during this period. Scientists often used them to study major changes in ancient life, especially around the boundary between the Turonian and Coniacian ages. There were many meat-eating sea snails, called predatory gastropods, which used their special mouthparts to drill into the shells of other creatures. Tiny single-celled organisms called foraminifera, especially the globotrunchanids, floated in the oceans and became very common. Sea urchins and sea stars, which are part of the echinoderm family, also did well. Small crustaceans called ostracods were everywhere. But interestingly, those species that put more effort into reproduction, especially males, were more likely to die out. A mysterious group of crustaceans called Thylacocephala disappeared by the end of the Cretaceous. Meanwhile, a big increase of microscopic algae called diatoms happened in the oceans. These had glass-like shells made from silica. However, freshwater diatoms did not appear until the Miocene epoch, much later. Another group of tiny marine organisms, called calcareous nanoplankton, became very important. These helped build up the seafloor and are useful today for tracking environmental changes in ancient seas. The Cretaceous was also an important time for bioerosion. This is the process where sea animals drilled into rocks, shells, or hardened seafloors, leaving marks that scientists can study. On land and in the oceans, Earth's shape and continents were changing a lot. The huge supercontinent called Pangaea, which had started breaking apart earlier, finished splitting up during the Cretaceous. The land areas that would become today's continents moved into their own paths, although they were still in very different positions back then. As the Atlantic Ocean grew wider, a series of mountain-building events, called orogenies, continued in what is now western North America. These included the Nevadon, followed by the Sevier, and finally the Laramide orogenies. Gondwana, the southern supercontinent, had started breaking up during the Jurassic period, but its splitting sped up during the Cretaceous and was almost finished by the end of the period. South America, Antarctica, and Australia all moved away from Africa, although India and Madagascar stayed connected until about 80 million years ago. This breaking apart created new oceans, the South Atlantic and the Indian Oceans, and also raised huge underwater mountain chains. These changes caused sea levels to rise all over the world. To the north of Africa, the Tethys Sea began to shrink. For much of the late Cretaceous, a large inland sea called the Western Interior seaway split North America into two land areas, Laramidia in the west and Appalachia in the east. This sea later shrank, leaving thick layers of marine rock between coal-rich deposits. In Africa, fossil records show that the continent was also split by a shallow sea during the Coniacian and Santonian ages. This sea stretched across what is now the Central Sahara and other parts of Central Africa, connecting the Tethys Sea in the north to the South Atlantic Ocean. Another shallow seaway existed between what we now call Norway and Greenland. It connected the Tethys with the Arctic Ocean, allowing sea animals to move between the two regions. At the peak of these high sea levels, called the Cretaceous transgression, about one-third of the land we have today was completely underwater. The Cretaceous is best known for its chalk deposits. In fact, more chalk was formed during this time than at any other period in the last 540 million years, which is the span of the Phanerozoic Eon. As underwater ridges grew and seawater moved through them, the oceans became full of calcium. This made it easier for tiny organisms like nanoplankton to build their calcium-rich shells, which settled on the seafloor and formed thick chalk layers. Because of this, rocks from the Cretaceous are well preserved and full of fossils. In North America, famous examples include the Smoky Hill Chalk Member in Kansas, which is full of sea fossils, and the Hell Creek Formation, known for its late Cretaceous land animals like dinosaurs. In Europe, important Cretaceous rocks can be found in the Weald region of England. In China, the Yixian Formation has given scientists many beautifully preserved fossils from this time. In the area that is now India, huge volcanic eruptions formed the Deccan Traps. a vast area of lava flows that started erupting in the very last part of the Cretaceous and continued into the early Paleocene.